Okay, last time, well, in general, we've been talking about how molecular machines work, and we talked about how they compare to macroscopic machines. And last time we talked about, in detail, about the DNA polymerase and what kinds of interactions account for the driving forces, the changes in Gibbs free energy from step to step. Most of that discussion revolved around this kinetic mechanism. And now what I've done is add to that kinetic mechanism the actual kinetic rates, as you can see here, for the binding step, for the fingers closing step, for the catalysis step, for the pyrophosphate release step, and finally for the fingers opening step. And the main conclusion or thing you should notice from those rates is that this one, the fingers closing step, is a lot slower than all the others, and therefore it's the rate limiting step. I pointed out before, but now we can see more clearly that what that means is that this part of the mechanism right here is the part that really controls the rate, the overall rate of reaction. After that, the steps are so fast that they really don't change the amount of time it takes to get around the whole cycle. So everything in the overall turnover rate, or the velocity of reaction, if you like, using the Michaelis-Menten terminology that we talked about earlier, is in these first three steps. And this basically becomes K-cat, or K2. This is K1, and this would be K-1 in the standard Michaelis-Menten mechanism. And what that means is that this overall five-step mechanism really behaves like a two-step mechanism and behaves like Michaelis-Menten. Here it is again. Here's the Michaelis-Menten mechanism. And here's the binding step for the DNA polymerase to an NTP. Then for the DNA polymerase NTP complex to close in this slow step, which would be K2, and then after that it's fast steps that don't change things much. And so yes, everything looks like Michaelis-Menten, and if you plot the velocity of actual replication, the actual rate at which nucleotides are incorporated into the DNA, versus the amount of substrate, that is the NTP concentration, then you get something that's pretty much a perfect Michaelis-Menten curve. And so from this point out, we can use the Michaelis-Menten model or mechanism to understand how the DNA polymerase works, with the understanding that when we do that, we're not looking at these later steps. We're basically just looking at these first two steps. We're looking at binding of the NTP to the polymerase DNA complex. And then we're looking at this fingers closing step as the K2 step. This fingers closing step is going to lead to Vmax mainly, right? Because Vmax is K-cat times the enzyme concentration. And this pair of steps to begin with, the binding is mainly going to contribute to Km. So when we're looking later, and we'll see, at Vmax, we're looking at effects on the fingers closing step. And when we are looking at Km, we're looking at effects on the binding, mainly on the binding of the nucleotide to the DNAP complex. All right. We're going to use those facts in a minute to understand how DNA gains its very high fidelity. But before we do that, let's sort of complete the basic physical chemistry by asking now not about the delta G's for each of these steps. So I put those delta G's in here in case you didn't see that. Here's one, for example. Here's another one, and so on. And they're all written in here, and you can look at these in the notes as you like. But we haven't talked about the kinetic barriers, especially for this step, right? This is the rate-limiting step. There's a big kinetic barrier there. Can we, by looking at the structure of the complex that's formed here, and also from our knowledge of what kind of interactions give rise to contributions to the delta H, and also what kinds of contributions give rise to delta S changes, can we understand why this step is slow? What is it about this step or that causes it to be rate limiting? And so let's look at that. Can we say something about the kinetic barrier from what we know already? And the answer is yes. Not in a quantitative sense, but at least in a qualitative sense. We can get some feeling just by looking at things. Given our understanding of the basic physical chemistry, we can get some understanding for what the transition state looks like, what the energy of activation looks like, and why this particular step might be expected to be slow. So we're going to look at the fingers closing step. We could look at all the other steps too, but fingers closing step is the most important one. It's also a little bit easier to understand than the others are. So for both reasons, we're going to look at it. All right. So what happens in the fingers closing step? Well, the fingers close. And I've said earlier that the fingers have a hinge, right? When the fingers close down, it involves bending the fingers domain down. That causes distortion of the native structure of the protein. That costs free energy. We can understand that as sort of an elastic deformation with a more or less of a hinge point. It's not a single point, but a hinge region at least within the protein. And if we think of it as sort of an elastic deformation, then that ought to obey a more or less harmonic relationship. In other words, as we bend further and further, the energy required to do that bending should go quadratically in the bending angle, theta. So I've defined this bending angle, and that's going to become a reaction coordinate later. So pay attention to that angle. It's just the hinge angle for bending the fingers domain. On the other hand, if we were to bend the fingers domain backwards, we'd also be going up in energy, right? When we start out, it's right where it's happiest. That's why it's sitting there. If we bend it either way, we're going to increase the energy of the overall thing. It's going to take some work, take some energy to bend it either way. And so it looks more or less like this quadratic harmonic oscillator potential. It's a very broad one, though, because the distances that we're moving here are quite large compared to atomic dimensions anyway. They are on the range of nanometers rather than angstroms. All right, but if we start bending this fingers domain down, pretty soon we're going to start touching the bottom here. And when we do that, the fingers are going to interact with the base pairs that are sitting there, as we've talked about already, and that means they're going to stick. There's going to be some free energy contributions that will cause the bent fingers to stay in place anyway, despite the fact that they're under strain and the bending has cost some energy. If they stick well enough, then they'll stay in place, right? If they don't stick well enough, then they'll spring right back. But if they stick hard enough, then they'll stay closed for at least until things change. And that we can understand as a potential energy that looks something like this, right? What that means is that as you increase theta here, you're increasing the bending. When you start to get to the point where the fingers are touching the rest of the protein and the DNA, there's going to start to be some sticking, and as you increase angle, that sticking will be favorable, so we'll go down in energy. And it gets stronger and stronger the better we go, the further we go. But if we go too far, then we're going to start sort of pressing the fingers into the protein. You don't want that. So we're going to have this narrow potential energy well that represents the sticking phenomenon between the fingers and the rest of the DNA. Well, we can combine these two pictures. One is bending, one is sticking. If we do both things at once, then we get a potential energy curve that looks like this. This says that as we start out at neutral here and we start bending, we go up in energy until we start sticking, and then we go down in energy, and if the sticking is strong enough, you can go even below to an energy that's below where you started, right? started out here, if it sticks hard enough to overcome the bending, then you get to lower energy even than you started with. And this should look familiar. That diagram should look familiar. It looks like a reaction energy diagram, right, from one of our earlier discussions of the Arrhenius theory or the Eyring theory. And in fact, that's exactly what it is, with the bending angle of the fingers acting as a reaction coordinate. I think this is the first concrete case where we've actually seen what a reaction coordinate looks like. And in this case, it's something that's kind of obvious. It's the bending of the fingers. And so what that means is this. If I think of the protein and the DNA, the protein-DNA complex, as just sitting around in solution, remember there's a thermal bath here with a temperature T. That means it's sharing energy in the form of fluctuating energy with the protein all the time. That means this fingers domain is fluctuating. The whole protein is fluctuating, in fact, but the fingers domain is what we're focusing on now. And if we think of those fluctuations as being fluctuations in the angle, then on this diagram, it looks like the system is wandering around near the equilibrium point where the fingers are happiest. But if you get very lucky, then some of these fluctuations can actually go in the right direction and with the right energy so that they actually get to the top of the hill in this reaction energy diagram, and that's the transition state, of course, right? It's the point where the fingers have bent far enough so that they're near the top of the bending energy that it takes to bend them that far. But they haven't quite started to stick. They're starting to stick, but they haven't really stuck hard yet. And if the system gets that far, if the fluctuations just happen to be lucky and happy enough to get that far, then you can get over the top of this barrier, and then you can stick hard, and then the fingers will stick closed. And then you've carried out the reaction that's necessary for the fingers closing step, right? This process where you get over this barrier is the fingers closing step. And that's what the barrier looks like, therefore. This is EA here, the energy of activation. And what's unique about this particular case is that you have to move quite a long ways. Instead of just moving half an angstrom or an angstrom or two, as in most really atomic scale reactions, elementary reactions. In this case, you got to move 8 or 10 angstroms before you finally get over the top of the barrier. And that means that's another thing that slows the thing down, the reaction, this elementary reaction down, or quasi-elementary reaction down. One thing is the height of the barrier. The other thing is the size of this region here, where you have to move quite a ways, which means you've got to, by chance, get a lot of lucky steps that move you far enough to get over the top of the barrier. Not only do the steps have to all be going in the same direction, they have to be gaining enough energy to keep going in that direction at every point. And then finally you get over the top of the barrier. So it's not surprising, given the physical structure and what we know about how much energy it takes to bend DNA, to bend protein and so on, that this step is particularly slow. It's also slow for a functional reason, as we'll see down below. I mean, you could redesign the protein to make this step fast. Why hasn't that happened? Well, we'll see why at the bottom, down below, because basically a slow step at this point is useful for selecting the correct nucleotide over a mispaired nucleotide. If you incorporate a mispaired nucleotide, you've got a mutation, as I said earlier, and you want to avoid as many of those as you can. So the protein is designed so as to avoid those mispairs, and one of the ways to do that is to make this fingers closing step slow. Another point that I think is worth making, it's just an aside, a quick aside, is that this picture that I've just outlined, where you have a reaction coordinate, in this case the angle, and the system is kind of moving or bouncing around or doing a random walk along that reaction coordinate and then eventually gets over a barrier, that's the set of physical ideas that are behind something called Cramer's theory. That's another theory for rate constants, along with Arrhenius theory and Eyring theory, the two we've talked about so far. Cramer's theory is a bit more complicated and requires more sophistication. It requires solving diffusion equations and things like that. That's why we didn't talk about it. But for systems like this, which are beyond the atomic scale, that have a pretty big, a large number of atoms involved, in this case in the large protein, and also move over quite a large different distance, then Cramer's theory is the appropriate and proper theory to use, and it leads to many insights into how these kinds of chemical reactions go. All right, now we've had a pretty complete picture of how this molecular machine works. There's many more things that could be said, but this is a pretty good picture. And just to summarize, here's the five-step mechanism again, starting from the open and empty polymerase. You bind an NTP, then the fingers close, then catalysis takes place, then the pyrophosphate, the leftovers from the NTP, get released, and finally the fingers reopen and the polymerase moves along the DNA, or translocates as it's called. The first set of steps is driven by the binding of the NTP, right? The NTP itself sticks here because it binds, it has a particularly high KD for binding to the particular arrangement of atoms that represents this state. And then the fingers close because now that the NTP is present, there's favorable interactions, there's favorable sticking interactions between the fingers and the NTP and the template base and the rest of the protein. And then catalysis takes place because everything's lined up to be perfect for catalysis at that point, as we've seen. And then you've got a new nucleotide incorporated, and the only bad thing, or the only thing left to do, is get rid of that pyrophosphate and reopen the polymerase. So that's what you do. You get rid of the extra leftovers of the reaction. You open the fingers and you move the the polymerase along the DNA, and that completes the turnover cycle. The second part of this, the second set of steps in this mechanism, is driven by the catalytic step and the pyrophosphate release. So basically, what that all says is that the overall machine is powered by the overall reaction, which is DNA plus an NTP goes to DNA with an extra base pair incorporated, plus leftover pyrophosphate. There's a free energy, a favorable free energy associated with that. But that free energy gets divided into little pieces all throughout the whole five-step mechanism. Little bits and pieces of that free energy are being released a step at a time so that each step can go. Each release of free energy powers a different step of the cycle. And finally, in the summary, the kinetics follows the Michaelis-Menten rate law because the fingers closing step is rate limiting, and we looked at why that's the case. All right, that's our first topic, which is understanding how the thing works just as a physical machine, not worrying about its biological function particularly, mostly just understanding it as a physical object powered by thermodynamics and controlled by kinetics. Now we're going to answer the second question, and let me say that up to this point we haven't been following the book very much because most of this material doesn't come from the book. It comes from my own research background, in fact. Now we're going to go to question number 2, which is the question of how the polymerase makes so few mistakes, even for a really lousy polymerase, a low fidelity polymerase like the HIV reverse transcriptase. It only makes a mistake about once in 10,000 bases, and that's necessary. The size of the genome of HIV-RT is about 13,000 base pairs, which means that if HIV-RT made more mistakes than that, then those mistakes would start building up in the HIV-RT genome, and after a little while, the genome would lose all of its genetic information due to mistakes, and there would be no more HIV-RT. So if you have a replicase for anything, even something that's not normally considered alive, like a virus, its replicase has to be good enough to replicate the genome with about one or fewer mistakes on average in that replication process. Well, E. coli has 4 million base pairs in its genome, which means it needs a minimum of about one mistake in better than a million, better than 10 to the 6th. And in fact, the replicase for E. coli is called Pol3, and it has an error rate definitely higher than a million, somewhere, I mean, in some cases, depending on exactly how you measure and so on, up to about 1 in 100 million, which means that you can replicate many genomes before you get even a single mistake, and that's the kind of thing you need in order if you want to keep your genetic information. So how does the polymerase do that? I mean, a 1 part in 100 million is a phenomenally low error rate. How does it do that? Well, there's two answers to that, and short answers, I guess. One is that the polymerase itself has a pretty low error rate. So 1 part in 10 to the 4 or 10 to the 5 per mistake, that's basically HIV-RT. HIV-RT doesn't have the second reason, which is a proofreader, but E. coli does. The second reason is, so the polymerase itself is really good, but then the polymerase, a lot of polymerases have what's called a proofreader, which is a second active site on the polymerase. Sometimes it's part of the same protein, sometimes it's an additional protein subunit that binds to the first protein. But what the proofreader does is basically check over what the original polymerase did, and if it finds a mistake, then it cuts that mistake out and causes the polymerase to redo that step. And it's good enough so that that increases or decreases the mistake rate by a factor of 100 or 1,000. And so overall, if you take the high ends here, 10 to the 5th and 1,000, then you get 10 to the 8th. One mistake in 10 to the 8th. And if you take the low end, 10 to the 4th and 10 to the 2nd, then you get at least a million, 1 in a million error rate. In other words, when you've got a proofreader present, you are able to replicate millions of base pairs at the very least, and maybe hundreds of millions of base pairs without making any mistakes. All the higher organisms, even bacteria, let alone eukaryotes and ourselves, have proofreaders and sometimes multiple different kinds of polymerases and also error correction mechanisms and what's the word? Can't think of the word. Anyway, other polymerases that correct mistakes, all in the service of keeping this fidelity very high. And the reason is, of course, it's utterly necessary. Any organism that doesn't keep its genome correct soon doesn't exist anymore. So how does this work? How does the polymerase do these things? One possibility, the first thing you should think of is, well, it's just really thermodynamically costly to make a mispair in the DNA, to make a mutation in the DNA. So one way to say that is, here's the reaction that's taking place, right? You've got a growing DNA, here's the template strand, here's the primer strand here going around, and you're adding a new NTP. If that NTP is correct, then you're going to get something like this, right? You're going to get an AT base pair at this last position. But if it's incorrect, then you're going to get something like one of these guys out here, an AC mispair, an AA mispair, an AG mispair. Those are mutations if we leave them in place. And the question is there enough thermodynamic free energy difference between this guy, the correct guy, and these guys to explain this very high fidelity rate? Maybe it just happens that creating this mispair is so thermodynamically unfavorable, has high enough delta G compared to the correct pair that explains the fidelity on its own. So how can we answer that question? Is the free energy difference between these guys high or small? Here's how. Here's the way it's been done, and probably the best way there is, given all the other things I could say. You consider two single-stranded DNAs that have correctly complementary bases at their tips, and when those two guys anneal to form a double-stranded DNA, there's a certain delta G associated with that, with a correct pair here. On the other hand, you can start with two single-stranded DNAs, anneal them, even though they have an incorrect pair at the end. And so you get a mispair at the end, and there's a delta G associated with that. It's still, I mean, the mispair doesn't stop this whole DNA from annealing together. It still anneals together just fine. And so you can measure the delta G of that annealing, for that annealing reaction. And then you can subtract this delta G from this delta G, and that would tell you how much energy cost there is to forming that mispair. And that's exactly what's been done. And here's the way it's been done. So here's the reaction. It's really the reverse reaction. So we're going instead from the single-stranded DNA to the double-stranded. Instead, we're going the other way. We're going from the double-stranded DNA to the single-stranded DNA. The reason for doing that is it's easy. You just start with the double-stranded DNA already in solution. You heat it up until it melts, right? That's called the melting reaction. And you can measure the the delta G for that process. And the reaction is an unbinding reaction, right? So it's got a KD. We can understand this just the same as we understood the protein plus ligand goes to PL, or really the other way around, right? The PL goes to protein ligand. We can understand it as a dissociation reaction. It's a complicated one between complicated molecules, but still, it's a dissociation reaction, and there'll be an equilibrium constant that is a KD, just the same as for a ligand-protein binding. How do you do that experimentally? Well, here's how it's usually done. You take what's called a melting curve, which means that it turns out that the absorption of DNA at around 260 nanometers in the UV is lower when the DNA is in the double-stranded form than when it's in the single-stranded form or when it's in the mononucleotide form. And that means that if you monitor the absorption of the DNA as you raise the temperature, what you'll see is that the absorption goes up in a melting curve like this. And when you're at low absorption, that's pure double-stranded DNA. That means all your DNA is in the double-stranded form. And when you're at high absorption, that means all your DNA is in the single-stranded form. If you stop halfway, or if you look at the point halfway in the middle, that's called the melting temperature. The temperature at which that occurs is the melting temperature, and at that temperature and only at that temperature, the definition of the melting temperature is that at that point you're halfway through the melting process, which means that the concentration of one of the single strands equals the concentration of the other single strand. That always has to be true, right? Because you're melting apart DNAs, there's equal number of strands no matter what. But also equal to the concentration of double strands in solution, because you're halfway through, right? You've melted half the DNA. That means the single strand concentrations are equal to each other, but also equal to the concentration of double strands. We'll use that fact a lot in the next step down. All right, so what you do is you measure a melting curve like this and note the Tm for a function, for a range of different possible DNA concentrations. It turns out, we'll see why below, that the melting point depends on how concentrated the DNA is in solution. If you put in a lot of DNA, the melting point's higher. If you put in very little DNA, the melting point's lower. And so you measure the melting point that you get in your melting curve, as you increase the concentration of the DNA in solution. That's your experiment. And now look and let's see why that works, why that's helpful to us. Here's why. Here's the KD for the dissociation, for the melting process. That has to be equal to E to the delta G for melting, right? That's the quantity we want, this delta G for melting, divided by R times the temperature, the melting temperature itself, right? So if it's a KD at the melting point, then Tm is the temperature we want to put in there. We take the log of both sides, the natural log of both sides, and we use the fact that delta G for melting is equal to delta H for melting minus Tm times delta S for melting. And you get this, right, that the log of the Kd for melting is equal to delta H over R times 1 over Tm plus delta S over R for melting. All right, so far so good. But we don't know the Kd over here, right? In fact, the Kd is going to change as the temperature changes. So how do we deal with that? Well, it's going to change as the temperature changes, but it's also going to change as the concentration changes. At the melting point, we already have that all these concentrations are equal. Well, Kd is equal to the equilibrium concentration of each of the two strands on top, divided by the equilibrium concentration for the double-stranded DNA on the bottom. And these guys are all equal, so this strand concentration and that divide out, and that means the Kd is just equal to the concentration of one of the strands. What is the concentration of one of the strands? Well, we don't know. We can't really tell easily from the absorption spectrum, but there's a trick. We know how much total DNA we put into the experiment at the beginning. Let's call that total CT. That's the concentration, the total concentration of DNA in solution. Whether it's single-stranded or double-stranded, it's all part of CT. And also the total amount of that concentration for single strands has to be the concentration of strand A plus the concentration of strand B plus 2 times the concentration of any double-stranded stuff that happens to be around, because there's 2 strands in each one of those molecules, right? So that means, since all these are equal, that means that the concentration that you put in is equal to 4 times the concentration of just one strand when you're at Tm, and not true at other temperatures. But that means that this Kd that we don't know is just equal to the total concentration that we do know divided by 4, again, only at Tm. And therefore, we have our overall relationship that we're trying to get here, which says that the logarithm of the concentration, total concentration of single strands that you put into solution is equal to this quantity, delta H for melting, divided by R, times 1 over Tm, plus this other quantity we want, delta S for melting, divided by R. And again, as many times in the past, this has the form of a straight line. If we plot the logarithm of the total concentration divided by 4 versus 1 over the melting temperature, then the slope will be equal to minus delta H over R, and the intercept will be equal to plus delta S over R. And that's exactly what people do. So you form one of these. It's basically a modified Van 't Hoff plot. Normally in Van 't Hoff, you vary temperature and measure the equilibrium constant. Here we, in effect, know the equilibrium constant, right, because it's closely related to the total concentration. And we measure the melting temperature at each point. So what you measure and what you already know are kind of reversed versus a normal Van 't Hoff plot. But other than that, it is basically a Van 't Hoff plot. And of course, you can always extract delta H and delta S from a Van 't Hoff plot, so none of this is particularly surprising. And here's an example of that kind of thing. The axes are reversed here. We're plotting 1 over Tm on the y-axis and the logarithm of the total concentration along the x-axis, but it's basically, I mean, if you kind of mentally turn this on its side by 90 degrees, you can see that these are curves that look like this, right? steep curves that look like this. And there's 4 different curves on here for different possible DNAs. Notice that this particular pair has a mismatch in the middle. It's got a GA pair in the middle. This particular pair of single strands also has a mismatch. You can see there's a G here in the middle, and that's going to have to try to match with one of the A's in the middle of this guy. So there's also a GA mismatch in that molecule. But then these other 2 pairs of molecules don't have any mismatch. They're good, and that corresponds to these 2. The other guys correspond to these 2. And so you can see that you can tell apart when there's a mismatch from when there's not. And that's how this whole, process works, or how this whole technique and methodology works. All right. I think I will stop there. The very next thing we're going to do is look at the results of these kinds of experiments. And this has been something of an aside up to now, but now we're going to look at the results of these experiments and see what they tell us about how much free energy difference there is in a mispair versus a correctly paired double-stranded DNA. And I'll just jump ahead one more step to say, here's the important column. We'll look at this more closely next time. And the bottom line is that there's only about 1 kilojoule per mole in creating a mismatch. A mismatch doesn't cost you very much free energy, only a little, maybe between 1 and 2 kilojoules per mole, which is not enough, as we'll see with a calculation down here, to explain the very high fidelity for DNA polymerase. So it remains to be explained. The thermodynamics do not explain the fidelity of DNA polymerases. It remains to explain where that fidelity comes from.